This is the outline for the conformations of alkanes, cycloalkanes. You already have the handout. That's the one with the nomenclature in it. Okay, so these go hand in hand. We're not going to get to those for another day or two, but we'll go ahead and get you that. I know a number of you are working ahead. That's very good because next week we'll be here soon. Acid-base chemistry. Pretty much we can pick up where we left off, but let me remind you of IR. Maybe on Friday I'll go over, we'll do some IR problems. Please be prepared to learn from that. Okay? Problems in the workbook. And then at some point, probably like Wednesday, we'll see if there's any questions about nomenclature. We're off on Monday, right? Okay, acid-base, warm-ups, etc. I will send out keys to the physical properties in the acid-base warm-up at some point. Although 1 through 4 on the acid-base warm-up are pretty much covered directly in the notes. The acid-base mechanism, we will use that. You should be learning that. Various effects, resonance. Resonance, very important. Any questions about lab? Lab reports due tomorrow and Friday. Come to lab. Questions? Yes.
For the references, did you want us to like do it in like NLA format or anything like that, or did you want
Information about reference requirements should be cleared in the workbook. Other questions? Was it not clear? If it's not clear, please ask, but I think it's clear. Other questions about lab reports that are due this week when you come to lab? Questions about what you observed? Anything that doesn't make sense? Yes. Thank you. Okay. Resonance. Okay. Pretty much that's for you to read. I pointed some things out there. We will continue to see resonance all along as we go. Resonance often outweighs other effects. It can be a very strong effect. For example, if you look at this compound known as succinimide versus this alcohol, much more acidic, much lower pKa. Okay, that's what pKa means, right? Let's see, what's the most acidic H here, CH or OH? OH. You'd rather have an O minus on oxygen than carbon. So the more electronegative atoms, that's where you're going to form your minus at. And so the H's on those typically create the OH. What's the most acidic H over here? Forget about that. It's only CH or NH. Would you rather have minus on carbon or nitrogen? Nitrogen. This has to be the most acidic. Unless something else is going on that makes the CH more acidic. I reckon that could happen. Okay, would you rather have a minus on O or N? Oh, so it seems like this might be more acidic, more willing to come off and become conjugate base minus. Well, no, it's not. This is much more acidic. Why? Resonance. Okay, because when this acts as an acid, let's actually use a base to take off the H and use our acid-base mechanism. What's your favorite base? Anybody? Sodium hydroxide, yes, it'll stand by. Okay, there are many other bases. So we got hydroxide, right? What's our acid-base mechanism? It's on the previous page or so. Start with these electrons. These electrons make bond to H. What happens to these two electrons? We move on to nitrogen as a lone pair. There's one lone pair to begin with there, right? So what does this give? Oxygen lone pair making bond to H, that's going to give, well, give that because the third lone pair is now bonded to the H. Well, lo and behold, that's water. What does this give? These electrons move there. The HN bond is being broken. We have N. One lone pair to begin with. Now what's there? A second lone pair. That's what this arrow means. These two electrons are moving onto the nitrogen. There's another lone pair. Now you have this. Well, what's the charge of this nitrogen? Because that's not typical nitrogen. Minus. Okay, so there you go. There's your product. Now the sodium sits here or it sits here. It's a spectator ion. You got to have a positive to balance your minus. There's your acid-base mechanism, as shown generically on that one page. Here's your conjugate base. The fact that this is so much more acidic, as by the pKa, implies what? That this is so much more stable than that conjugate base. Why? Well, that's oxygen. It should be more stable, right? Oh, wrong. This was actually more stable. Why? Resonance. Okay, can you show resonance structure? Or can you understand that what's the hybridization of the nitrogen? Hybridization of the nitrogen.
sp2.
sp2. Anytime a lone pair is next to a p orbital, it's going to want to be in a p orbital. Got p orbital here and here. Okay, so what you got here is nitrogen. I'm just going to do the upper one, I reckon. We're going to put the lone pair in a p orbital. But see, you also have p orbitals up here. There's the pi bond. This is trigonal planar. If it's sp2, it's trigonal planar. See the three bonds, the three dashes or whatever, that's trigonal planar, but there's a lone pair coming out here. But one of the lone pairs is in a p orbital interacting with the neighboring p orbitals, but there's also a p orbital here. That lone pair is conjugating with all these other p orbitals. Now we can also actually just show a resonance structure where we say these electrons move here, these move up, resonance arrow, and we get something that looks like hopefully you can see down here. You can't see this though. A lone pair left, and now that's a minus charge there. And we have delocalized the charge onto the oxygen. This charge is not just sitting on the nitrogen. It's delocalized by resonance. Important things here. Understanding there's a lone pair in a p orbital. Understanding the overlap of the p orbitals that it does have. Understanding the arrow movement. If I take these electrons and move them in, I'm moving it in and making the other bond. If I move these up, I'm moving them up to become a third lone pair. So this arrow movement gives this, the essence of resonance structure. Then charge. That's a standard nitrogen. This is not standard oxygen. That's going to be charged. You've got to be able to determine the charge. Ultimately, this is just an example of showing you that resonance can trump other effects. Nitrogen is not more electronegative, but the charge is delocalized by resonance. Question?
Does it only work if the pairs with p orbitals? Or
Yes, only if it's, as opposed to what?
like I was thinking like if it's like an sp orbital?
Does an sp3 atom have a p orbital?
No.
No. Resonance is p orbital overlap. If the atom doesn't have a p orbital, then it can't be doing resonance. Right? Good. Okay. You're not going to understand resonance and everything now, but this should fit exactly what we talked about up there. And it's just an example of the power of resonance. So cinnabides are fairly acidic because of that resonance. Question?
Does resonance only work if the double bond is directly adjacent to the atom you're looking at? But you would jump multiple bonds, so you had.
I think you're generalizing a bit too much. I'd have to see the example you're talking about.
Resonance is p orbitals lined up. I mean, look, p orbital, p orbital, p orbital, p orbital, p orbital. I tried to draw them there. This is, that pi bond's coming from two p orbitals, right? Same thing here. But if we can make this guy have a p orbital, then you got 5 lined up. And we said already, anytime a lone pair is next to a p orbital, it's going to want to line up and be in a p orbital. Okay. The next effect we'll look at is hybridization. Hybridization effect. Look at the acidity of these hydrocarbons. These are just hydrocarbons. An H on an sp carbon is more acidic than an H on sp2 carbon. For example, here, this H on sp2 carbon. And that's going to be more acidic than H's on sp3 carbons. So all these H's are on sp3 carbons. Hopefully you quickly recognize this hybridization. Why is this guy more acidic? Well, it's because it's on an sp carbon. That doesn't answer our question. It's important to answer questions a little bit more deeply. As I'm erasing, I'll point this out. For example, why is Bill Gates rich? You would not want to say because he has a lot of money. It's not answering the question. That's really nothing more than a restatement of the question. Then I have to turn around and say, well, why does he have a lot of money? It may or not be applicable here, but keep that in mind when you're answering questions. Okay. So why, first off, we want to consider the conjugate base, right? This acts as an acid, the conjugate base will be this. Versus if this acts as an acid, it would be this. Well, this carbanion is more stable. And that's implied by the fact that this is more acidic. Why? Well, this carbon took on an extra lone pair, or a lone pair would have acted as an acid. Negative charges inherently are not stable. Things want to become more neutral. Charges want to kind of come together and neutralize each other. What type of orbital is this lone pair in? It's in an sp orbital. If you graph that, you should know that's in an sp orbital. This LP is in what? The lone pair is in an sp3 orbital. You got to know that. Okay. Which lone pair is closer to the nucleus? This one, it's 50% S. It's only 25% S. 50% S means that that hybrid looks more like an S orbital. The electron density can approach the nucleus more. P orbital, there's no electron density at the nucleus. The electrons are closer to the nucleus, they're closer to those protons. And the charge is not as separated. And as the electrons can get closer to the nucleus, they're more stable. So this lone pair is more stable, thus the carbanion is more stable than this over here. Thus, this H is more willing to come off as an acid and get this. Okay? This is a hybridization effect. And understanding the percent S character, and thus what does that do for you, and what kind of argument can you make? I sometimes say the electrons are closer to mama. Okay? They're closer to the nucleus. They're safer there. They're more stable there. Okay, questions about that? I did that with carbons, but you can apply that to lone pairs on any atom. But this is application of our hybridization. So take it one step further and say, okay, we understand hybridization. Now can we understand closer to the nucleus and then yeah, okay. But as we build, if you don't understand A, B, C, and D, you're not going to be able to grasp E and F and G and on down the line. So, okay, so those are the 4 effects. Let's look at bases. You taught in Gen Chem that bases may be accept in H. I don't like the terminology. Bases take H's. We want to be more active about it. Okay? Bases take H's. Now with the hydroxide example we showed here, we showed hydroxide as a base. Hydroxide took the H from succinimide, right? We can show this carbanion taking an H from water. It's our same old acid-base mechanism, although I didn't circle the electrons. These electrons do what? They take the H, so the carbon makes a bond to H. What does that give? Well, carbon now bonded to H. That used to be a lone pair. Now the lone pair is bonded to the H nucleus. So we get that outcome. Well, what happens over here? These electrons move on to the atom as a lone pair. So now the oxygen has how many lone pairs? 3. It's a minus charge. Okay? So you should be able to look at any acid-base mechanism and do the acid, and we're going to need acid-base reaction. Do the mechanism, show the outcome, instead of trying to just memorize an outcome. Okay? You can become very simplistic in this regard. So this is obviously the base. Water is acting as an acid. The base took the H, and here's your outcome. Of course, strong bases will have a high pKa for the conjugate acid. Whoa, what's all that mean? As we move forward, we'll talk about pKa's. Each side of an acid-base reaction has an acid or a base. Over here, this is the base, that's the acid, because it's the one giving up the H. And with the acid, you can give a pKa to describe its acid strength. Same thing over here. If we went this way, and all acid-base reactions were theoretically equilibrium, if we went that way, which compound would be the acid? Well, this one, because it's got the H. Because if you go this way, it loses one, so it must have acted as the acid. And this was the base. And the acid should have a pKa. And we know that a CH is not going to be that acidic, so the pKa is very high. And an OH is going to be more acidic, and its order is 16. So you need a pKa for each side. Bases, though. In organic chemistry, we don't use pKb. We actually use pKa's for bases. But when you give a pKa for the base, it's actually referring to the conjugate acid. Okay? For example, we could say this is pKa greater than 40. I'm not going to say anything else about that now. We'll discuss a little bit later. It's just we got to be thinking about pKa's and equilibria and what the things mean. Before we get there, though, let's look at bases. First off, bases do not have to be anions. For example, ammonia is a decent base. Okay, has a pKa of approximately 10. Put it in water, we can show an acid-base reaction. If ammonia is going to act as a base, that means it takes an H. So these electrons can take an H here, the same old acid-base mechanism. But the ammonia becomes what? There's an H3, but the lone pair is now bonded to another H. And so it becomes this. Well, that's an atypical nitrogen. It's a positive charge, right? So that's how we get the ammonia. Of course, we generate hydroxide. And make this here. It's the same mechanism we did up there. Difference is here the base was not charged, but the result became charged. Okay, at this point, let's look at base strength, particularly looking at nitrogens. Because as we'll say on one page, on the summary page, good bases are either anions, like hydroxide, or the C minus. Anions tend to be good bases. The only neutral atom or type of molecule that's going to be a good base is a neutral nitrogen compound, like amines. Okay? sp3 nitrogen is going to be your most basic. And then the sp2 nitrogen will be less basic, right? Hybridization effect. And one thing we'll say is if the lone pair is in a p orbital, it's not going to be basic. Statement we're going to make, because lone pairs that are in p orbitals are busy doing resonance. They're not interested in acting as a base. Okay, with those two things said, let's look at these and see if we can predict which neutral nitrogen compound is the, well, many of them are, which is the strongest base. We also have to use our 1 through 4, hybridization effects, resonance effects, etc. Inductive effects. So which one's a stronger base? Ammonia or methylamine? And what's your argument? Obviously the difference is the methyl group. Now if we're going to make the nitrogen more basic or less basic? What does a methyl do?
Kind of pushes the electron towards it.
sp3 carbon donates? Yeah. Okay, you can draw a donation by the methyl, yeah. So what's that going to do to the basicity of the nitrogen?
Keep it more unstable.
Make it more what?
Unstable. Or willing to
Why would it make it more unstable?
It's pushing it negative.
It's like in a net to try to pull it so it's more stable. Now it's going to push it that away.
Yeah, the donation. Yeah. Here's how I say it. When something's acting as a base, we're looking at the lone pair. The lone pair goes and finds the H, takes the H. Okay. The lone pair is electron density. Okay. Now this electron density thing can be perturbed by donation and withdrawing. We're pumping electrons towards that nitrogen lone pair. So here's the lone pair, okay? Like neon light glowing. All right? Somebody pumps some electrons toward me. You were methyl. Ooh. Now my lone pair is even more invigorated because he pumps the electron density towards my lone pair. Okay, that's how I think about it. Okay? Electron donation, by inductive, we know that, increases electron density on nitrogen. How about if we say something like that, right? More electron density on nitrogen, where the lone pair is, electrons are minus, so there's more minus on the nitrogen. Okay? You got to get this idea that molecules are not just static there. The electrons are perturbed. Just because we draw bonds don't mean that we can't increase the electron density at this lone pair region. Okay? This is more basic. On the other hand, we can make another molecule. What if we had H, and put an F on the nitrogen? Compare this to ammonia, more or less basic. What do we got? We got an F. What does it do? They're very electronegative, inductively withdrawing. Okay, is this going to be more basic than ammonia? No. Here's my lone pair. Somebody withdraw. I'm not as interested in the proton anymore. You took my electron density, right? Okay. Number 2, which one's more basic? So this was an inductive effect, right? Actually, yes, these effects are going to be just the opposite of stabilizing a minus. Okay, they're both nitrogens. This is the hybridization effect. This lone pair is in what type of orbital?
SP3.
sp3. This lone pair is in what type of orbital?
SP2.
Okay, which one's going to be more basic?
SP3.
One of the sp3. Less s character, so it's not held as tight to the nucleus. More s character, closer the electrons are held to the nucleus. That's the same thing we set up there. Except up there we were looking at acid, so we're looking for the most stable anion. Way back up here. Which one's the stronger base?
One left. Or right.
One on this left?
Yeah.
Yeah. Stronger base. It's at least stable. Those electrons are not held too close to the nucleus and sort of relaxed. They're out there, high energy electrons. So they're going to be more willing to want to take an H and go back there, which is the opposite of this guy wanting to come here. So you got to know which way you're going, acids or bases. Yeah. Okay, your sp3 nitrogens are your most basic nitrogens. sp2, slightly basic. We'll call them basic. When you get sp3 nitrogen, they're almost not basic. sp nitrogen, almost not basic. Okay, other example. Which one's more basic? Left or right?
Left.
It's sp3. What type of orbital is this in?
Yeah.
P orbital. Okay, non-basic. As we said at the opening, a lone pair that's in a P orbital is typically non-basic. Why?
Busy doing
The lone pair is busy doing
resonance.
resonance. It's in a P orbital, and it's interacting with the P orbital next door. And since it's interacting with the P orbital next door, it's not that interesting in interacting with your 1s orbital of your hydrogen. The interaction of the lone pair with the next door P orbital really occupies the lone pair. It's just not. There will be some exceptions. There are some times when a P orbital lone pair will have some basicity, but in general, no. Question? Looking at the end instead of the what? Because the end is the basic atom. We're talking about which one of these is going to be more likely to go react with the ethanol. Which one of these is more likely to go do this? This one, because this guy, this lone pair is doing something else. It's conjugated. It's not interested. These electrons are not interested in doing anything else. Let's see. Or we'll go this way. These are not nitrogens. Which one's more basic? F minus or Cl minus? Cl. F minus, more basic. Why? That's that size effect. Which one's more stable? Cl minus is more stable, because it's larger. Since it's more stable, that means it's happy being minus. F is not as happy being minus 3, even though it's the most electronegative atom on the periodic table. It's because it's so small that it can't handle the minus as well as the bigger atoms. Now it handles it much better than oxygen and nitrogen and carbon. Remember, it's size, so, I mean, HCl is more acidic. Which is more basic, ammonia or water? This is an electronegativity because they're both sp3 lone pairs. Which one's more basic? What's the difference between oxygen and nitrogen?
Oxygen is
Oxygen's more electronegative. What does that mean?
more stable.
It means it holds its electrons tighter. Okay? I'm an oxygen. Here's a lone pair. I hold it tight. Why? Because there's attraction. I have more protons. Okay? Here's a nitrogen lone pair. Well, the nitrogen doesn't hold it as tight. I say this. Nitrogen's not a good parent. Oxygen's a much better parent. It holds its kids close to the nucleus. It's electronegative. Nitrogen's a bad parent. Okay? Lets its lone pairs get out there and get in trouble. Go react with protons. Okay? More electronegative, the more the nucleus is going to pull the lone pairs closer. Ammonia is a stronger base. In fact, ammonia is a pretty good base. Like we said, a sp3 nitrogen is about the only neutral compound that's a good base. Water is not a good base. Which is a stronger base, this carbanion or this one? Well, this has the extra sp3 carbons. What do? Donate? Is that going to stabilize the anion or make it more electron rich? More electron rich, and thus more prone to finding an H+. More basic. Okay, inductive donation, electronegativity, size, hybridization, inductive donation, hybridization. Really, this is resonance, because this lone pair is resonance, that lone pair is not. So we can assess stability of anything using these 1 through 4. The point where you guys are going to get confused on until you figure it out for yourself is, okay, is this thing acting as an acid? Is it acting as a base? You got to figure out that you can't just memorize or you're going to lead to confusion. You got to ask the appropriate questions. As we mentioned, neutral nitrogen compounds can be basic. There's lots of natural products out there in the world, kind of semi-complex molecules that are found in nature. A lot of these contain a basic nitrogen. And these are called alkaloids. The basic nitrogen is kind of alkaline-like. It's basic. Now, it's not as basic as hydroxide, but it's still as basic. This just shows have you ever heard of alkaloids? Is that term mentioned in biology? Ever? Okay. A number of alkaloids have biological properties. Some of them have like psychedelic properties, like some alkaloids in mushrooms. Anybody have experience with these? Are you experienced? This is just a variety of them. You know, cocaine is an alkaloid. You see this basic nitrogen here? It's an sp3 nitrogen. Some of them may be more medicinal, like atropine.
That's just the term alkaloid. You can't go through organic chemistry without knowing the term alkaloid. Okay. Recognize the basic nitrogen. For example, up here, which nitrogen is basic in ergoline? Or LSD? Which nitrogen of LSD is basic?
The what?
Top, middle, or lower?
Middle.
Middle, yes. This is basic nitrogen. The other two are not basic. The other two, the lone pairs are in p orbitals, right? Either the amide or this is kind of a heterocyclic nitrogen. Lone pairs in a p orbital. Lone pairs in a p orbital. There's your basic nitrogen. Okay, predicting acid-base equilibrium. Okay, this is the same reaction we showed on the other page, and I started talking about pKa a little bit. I believe it is, right? Okay. Let's look at equilibrium. Which side's going to be favored, et cetera, et cetera. Each side's going to have an acid, right? pK over here is water. Over here, the acid is methane, because if it went this way, we're saying that the base takes an H from methane to get over here. This guy has the H on this side. Water has the H on that side. pKa for each. Okay? Which side is favored? The side with the weaker acid is going to be favored. Which is a weaker acid, water or methane? You should know that from looking at structure. But you can also know that from looking at pKa's. Much higher pKa. Weaker acid. This side is thus favored. By how much? It's favored by the difference in your pKa, your two pKa's. The difference is 10 to the 24, at least. What is 10 to the 24? That's like 100 gazillion. Okay? So the equilibrium, you have 100 gazillion of these and only one of these. I drew this sort of equal, but in actuality, it's like this, right? Right, is highly favored. It's favored by 100 gazillion. Difference in your pKa's. Okay, let's look at another example. When you put that carbanion in water, it's gone. It's just going to form methane. It's going to take an H. Boom. What if we take this acid and put it in water? Well, first off, how do I know this is an acid? Because up here, that was a base in water. Carboxylic acid. Okay? Well, also kind of gave, on the sheet I gave you a pKa. I showed you the outcome. The fact that this became minus must mean that this was the acidic proton. And water took the H. Okay? Let's draw that bond in. Of course, our acid-base mechanism, if this is the base, the lone pair takes the H. These electrons stay behind. And what do you get? When those electrons stay behind, you get this, and that's a minus charge. Of course, if we drew this out, it would be oxygen with now 3 bonds to H, 1 lone pair left, and that's a plus charge. So our acid-base mechanism allows us to predict this. pKa of a carboxylic acid is about 5. You should pretty much know that. pKa of hydronium ion is less than 0. Okay? Which side's favored? 5 or 0? 5, the weaker acid. By how much is this side favored? The difference, which is 10 to the 5 or more, depending on what that over there actually is. So, will water completely deprotonate acetic acid? Will it completely go that way? No, it will not. On the other hand, you can say something like this. Will this guy completely ionize in water? No, it will not. That's why it's called a weak acid. Question?
Why does the reaction favor the side of the weak acid? Why does the reaction favor the side of the weak acid?
If this side was favored, it's an excellent question, but the answer may be, well, I can tell you because these two molecules are more stable than these two. Okay. But we need to get more specific. For example, if you're saying this side's favored, you're saying this carbanion versus this. On the other hand, let's say if this is HCl plus water, what does that give? That's going to give Cl minus plus hydronium ion. You do your acid-base mechanism. Water takes the H. Okay. Now this is actually favored because pK of HCl is like -7. If we say this is 0 or so, I mean, these numbers are not strictly correct. But if that's -7 and this is 0, then this side's favored, right? Then you have to say, well, why? The reason why is because Cl minus is so much more stable than this. And then you have to say, well, why? At some point, you got it. It's a relative comparison. I think it's a very complex thing. Ultimately, though, the site's favored because the two species are more stable in that form than the other form. And you have to look at individual cases. You keep looking at it. Every time you do it, assess. These numbers imply that Cl minus is much more stable than this minus. Then you have to make arguments. Well, Cl minus is more electronegative, is larger than O. Probably it's more electronegative. Then you have to say, well, this has resonance, and that does it. You know? Well, keep asking. Because ultimately, the answer is that's the answer, and we have to be able to make arguments. And ultimately, that's a lot what we're about here is making arguments to fit experimental evidence, and then be able to make those arguments in testing format and reports. Okay. So, do one on your own. Actually, I already did that for you earlier. Okay. Already did this one, but we didn't assess the pKa's, which side's favored. You already have this, right? We did it over there earlier. We're going to get this minus plus what? Plus water. pKa of that is 8. What's the acid over here? H2O. Its pKa is 16. Which side's favored? 8 or 16? 16. This side's favored by how much? Favored by 10 to the 8. Okay. Hydroxide is strong enough to deprotonate this guy pretty much fully. Because at equilibrium, we have one of these and 100 million of these. Turn that into percentage, it's what, 99.999%? It's pretty much complete. Okay, our pKa's tell us that. There we go. Please do the remaining remaining 3 here. We will then look at the role of pH. How does pH influence the equilibrium? And that will be the Henderson-Hasselbalch equation. Okay. In the back, please note that I've summarized a number of these points, okay, on the back 2 pages. We got a couple of minutes. Questions on acid base that we've covered this far? What was the original question about acid base that I said maybe we could answer today?
I'm just confused about the chemical formula.
Is saccharin an acid or a
Yeah.
base? Sodium saccharin.
Sodium saccharin.
Sodium saccharin, okay. You have the structure? What page is that on? Okay, acid or a base? What are good acids? The only H's in this compound are on carbon. You agree? Is a CH going to be that acidic? No, it's going to be very rare to have a CH that's acidic. You don't want to make a C minus. You want to make something like an O minus or N minus or Cl minus. But the only way you can have a Cl minus is if you start with ACl. You can't have anything else, only chlorine. I don't see acidic H there. Okay. Is sodium saccharin a base? What do we say were good bases?
Anions.
Anions or neutral nitrogen? Do you see an anion? Do you see an anion?
Well, right now it's a salt, but if you took out the sodium, it would.
What do you mean right now it's a salt? Do you see an anion?
No.
Everybody sees an anion? See any anions here? Why no?
Yes, secondary compounds, yeah, sure.
It's an ionic compound. Is it an ionic compound?
Yeah.
Yeah.
So, but you're saying there's no ions. Yeah, it's ionic. Ions. Okay. Instead of sodium Cl, this is sodium whatever. That's Na plus and N minus, right? It's a nitrogen anion, which is an ion. And a salt is what? It's an ion pair. It's 2 ions. What's a good base?
Anions.
Anion, which is a negative ion. Do you see a negative ion?
Yes.
Yes, I see one. Those are typically good bases. That's a good starting point. Some may not be. I minus is not a great base, it's so very stable, but it's the, okay. Yeah. Even if that nitrogen was neutral, well, if it was neutral, it would, it'd be p orbital. Other questions? But the idea of anions and neutral nitrogens, that's one of the summary. There's like 10 summary points on that page. Okay? All right. All things are summarized there. I can't just stand up here and read the summaries to you. Okay? Question?
So on the laboratory, you want to show the acid base reaction with this class. Do you want to
If it says show the reaction, then yeah, you got to show it.
Just leave some space and then draw it in.
I mean, you can include it in your report. Just leave a space between your text. You need to draw something in. You can take off if you like. If there's any other questions. Okay, guys, have a good day.